There is a sound that peat makes when a blade cuts through it. It is not the sound of mud. It is not the sound of earth giving way the way earth gives way when a shovel finds clay or sand or ordinary, forgiving ground. Peat makes a different sound, a wet, pressurized exhale, like something that has been holding its breath for a very long time has finally been given permission to let go. And on a gray October morning in 1950, in the low, fog-draped moorlands of Jutland, Denmark, a farmer named Viggo Møller Christensen driving a mechanical peat cutter through the Toland Fen heard exactly that sound, and the world of archaeology was never quite the same afterward. But we are not here to talk about the body he found. We are here to talk about the blade, because across hundreds of sites in Denmark, Sweden, Germany, Ireland, and the United Kingdom, from the Illerup-Odal Valley to the Thorsberg Moor to the great raised bogs of County Roscommon, archaeologists have been pulling something out of the peat that defies every clean, comfortable narrative that mainstream history has ever tried to tell about ancient Europe. They have been pulling out swords, not corroded, not shapeless, not reduced to the orange dust of oxidized iron that is the fate of every other piece of Iron Age metalwork found in ordinary soil. These swords are different. These swords emerge from the peat with their geometry intact, their surfaces retaining the texture of hammer blows laid down 2,000 years ago. They're steel, and steel is precisely what it is, exhibiting internal molecular structures so sophisticated, so deliberately engineered, that when modern metallurgical scientists first subjected them to X-ray diffraction and scanning electron microscopy, more than one researcher reportedly had to put down their equipment and stand very still for a moment, because what they were looking at could not, according to everything the textbooks said, actually exist. This is the story of impossible metal. This is the story of a technology that history said could not exist, preserved in the one environment on Earth that could protect it from the ravages of time long enough for us to hold it in our hands and ask the question that changes everything. Who were these phantom blacksmiths? And what did they know that we forgot? Let us begin with the insult, because every great historical revision begins with an insult that turned out to be a lie. Julius Caesar wrote about the Germanic tribes north of the Rhine. Tacitus wrote about them. Roman military commanders, provincial governors, and imperial propagandists all had occasion at one point or another to commit their impressions of the peoples of Northern Europe to parchment, and the portrait they painted was remarkably consistent across 2 centuries of Roman commentary. These were, the Romans agreed, brave peoples, fierce, admirable in certain limited respects, but fundamentally backward, fundamentally pre-civilizational. People who lived in forests, who had not yet grasped the concept of the city, who lacked the intellectual architecture to build the things that Rome built, the aqueducts, the forums, the roads that ran in perfectly straight lines across thousands of kilometers of conquered landscape. The Romans called them barbarians. The word comes from a Greek root that meant, essentially, people whose speech sounds like noise, bar bar bar, people who could not articulate the complex truths of philosophy and science because They had not yet reached the rung of the evolutionary ladder where such articulation became possible. And this portrait, repainted and reframed by every subsequent century of European historiography that drew on Roman sources as its foundation, became the default operating assumption of mainstream archaeology for a very, very long time. Pre-Roman European tribes were primitive. They lacked systematic knowledge. They worked metal by brute instinct rather than by science. They could not have possessed the kind of empirical understanding of thermodynamics, carbon chemistry, and metallurgical process that producing advanced steel requires. 'Cause advanced steel, real steel, precision steel, steel with controlled and deliberate microstructures, is an achievement of the industrial era. It requires blast furnaces. It requires temperature gauges. It requires a level of technical abstraction and systematic knowledge transfer that oral cultures, by definition, cannot sustain across generations with sufficient fidelity. This is what the textbooks said. This is what the museum plaques said. This is what every undergraduate archaeology survey course said in every university, in every English-speaking country for the better part of 2 centuries. And then they scanned the Illarop-Odal blades, and the textbooks were wrong. The Illarop-Odal site in central Jutland is not a dramatic location. It is a former lake bed, or, more accurately, a former lake, since the lake that existed here during the Roman Iron Age has long since been filled in by 2 millennia of biological accumulation, leaving behind the characteristic dark, spongy, anaerobic environment that we call peat. Farmers worked around it. Roads were built beside it. The town of Skanderborg grew up at a respectable distance, and below the surface, disturbed by nothing more violent than the occasional weight of waterlogged moss, a deposit of weapons and military equipment lay waiting in the cold, acid dark. When systematic excavation of the site began in earnest in the 1950s, and continued with increasing sophistication through the 1970s and 1980s, what emerged from the ground was staggering in its scale. More than 15,000 individual objects: swords, shields, spears, lances, bows, mail armor, cavalry equipment, personal ornaments. The deposit represented not a single event, but a series of major votive offerings spanning roughly 200 CE to 500 CE, a period of 3 centuries during which, on multiple occasions, communities brought enormous quantities of military equipment to this place and committed it to the water as a deliberate, organized, and clearly ritualized act of destruction and consecration. But the weapons themselves, and specifically the swords, are what concern us here. When metallurgists from institutions including the National Museum of Denmark, the Technische Universität Berlin, and later the Massachusetts Institute of Technology began subjecting individual blades from the Illarop deposit to non-destructive analysis techniques that had not been available to earlier researchers. What they found forced a complete and humbling revision of the conventional understanding of Iron Age European technology. The blades were not made of iron, they were made of steel. Not accidentally, not as the result of some lucky contamination in the smelting process. Deliberately, purposefully, with a degree of technical control that implied not merely the possession of certain skills, but the possession of a systematic, transmittable, empirically refined body of knowledge about the behavior of carbon in iron. Knowledge that the official history of metallurgy insisted did not exist in Northern Europe until the medieval period at the very earliest, and in certain forms not until the Industrial Revolution. The carbon content of the Illyrup blades was not uniform. This is the critical detail. This is the detail that changes everything. Modern steel production achieves its extraordinary range of mechanical properties: hardness, flexibility, tensile strength, edge retention, by controlling the distribution of carbon within the iron. Matrix, low carbon content produces soft, ductile metal. High carbon content produces hard, brittle metal. The art, and it has always been at its highest expression, an art of making a blade that is simultaneously hard enough to hold an edge and flexible enough not to shatter on impact, is the art of getting different zones of the blade to have different carbon contents, managed with enough precision that the final object achieves the optimal combination of properties across its geometry. The Illyrup smiths were doing exactly this. The core of each blade, the structural spine that ran from tang to tip, was forged from iron with low carbon content, giving it the toughness and flexibility to absorb shock without fracturing. The edge zones, the thin, beveled strips of metal that would carry the actual cutting function of the weapon, were built from iron with dramatically higher carbon content, hard enough to be given a razor edge and to retain it through combat use. And these two materials were not simply placed side by side. They were forge-welded together at temperatures and with timing that the smiths had determined through generations of accumulated, tested, refined empirical knowledge, in a process that modern metallurgical science calls structural composite steel manufacturing, and that the textbooks say was invented during the Industrial Revolution. The textbooks are wrong. The Illyrup Odal smiths were doing it in the 3rd century of the Common Era, in the forests and workshops of what is now Denmark. Without thermometers, without spectrometers, without written records of any kind, guided entirely by knowledge that had been accumulated through observation and transmitted through practice across a chain of master and apprentice relationships, extending back into a past that the archaeological record can illuminate but cannot fully trace. And here is the question, the open loop that we are going to spend the next 2 hours closing, that should be echoing in your mind right now. How do you arrive at that level of technical precision without the scientific infrastructure that we have always assumed is its prerequisite? And more importantly, what happened to it? Where did this knowledge go, and why did it go there? Because the Iron Age did not last forever. The workshops that produced the Illyrup blades are gone. The masters who taught the apprentices are gone. The knowledge that made the impossible possible disappeared. Deliberately or accidentally, or through the catastrophic interruption of the social structures that sustained it. And when European metallurgy re-emerged from the chaos of the early medieval period, it emerged at a significantly lower level of technical sophistication than the one it had lost. That is the mystery. That is the story. And we begin to understand it by going into the swamp. To understand why the bog preserved what everything else destroyed, you have to understand what a peat bog actually is. Not what it looks like from the surface. A low, wet, unassuming stretch of moorland that farmers historically avoided and travelers historically feared. But what it is chemically, biologically, and physically. Because the bog is not a passive receptacle. It is not a neutral container that happened to receive and retain these objects by accident. The bog is an active preservation system of astonishing sophistication, running continuously, without any human intervention, driven by the biochemical properties of a single genus of moss that covers the northern reaches of 4 continents, and whose preservation capacities were being exploited by human communities long before anyone understood the mechanism that made exploitation possible. That moss is sphagnum, and what sphagnum does to its environment is nothing short of revolutionary. Living sphagnum moss grows at the surface of the bog, reaching upward toward the light and moisture of the northern sky. As the living layer grows, the dead layers beneath it compact under their own weight, slowly becoming denser, less aerated, less connected to the oxygen supply of the atmosphere above. This is where the chemistry begins. Decaying sphagnum releases a compound called sphagnin, a polysaccharide with a remarkable and, for our purposes, extremely important property. Sphagnin is a powerful chelating agent, meaning that it binds to metal cations in the surrounding environment with an avidity that effectively starves the local chemistry of the positively charged ions, calcium, magnesium, potassium, that microbial life requires to function. Without those ions, without the mineral nutrients that bacteria depend on for their metabolic processes, bacterial decomposition in the bog environment is dramatically suppressed. The microorganisms that would, in any normal soil environment, reduce a human body to bare bone within a decade and a piece of organic material to nothing within a century, are simply unable to operate at the scale that decomposition requires. The bog, through the action of sphagnum, has effectively built a natural antibiotic environment that extends throughout its entire depth, from the living surface moss all the way down to the lowest strata of fully compacted, nearly petrified ancient peat at the base. But sphagnum is only part of the story, because alongside its chelating function, decaying sphagnum also releases substantial quantities of humic and fulvic acids, organic acids, that drive the pH of the bog water to levels so extreme as low as 3.5 to 4.0 on the pH scale, roughly equivalent to vinegar, that the acid environment provides a second, complementary mechanism for the suppression of biological decomposition. Most bacteria cannot survive in an environment that is acidic. Most fungi cannot survive in an environment that is acidic. The bog, in its most mature and fully developed form, is a system that has used biology to create chemistry that kills biology. And the result is a preservation environment of a kind that exists nowhere else on the surface of the earth with the same combination of properties. There is, however, a complicating irony in the peat bog's preservation chemistry. the same acidic environment that protects iron from the oxidative destruction of atmospheric rust, does something quite different to the calcium phosphate matrix of human bone. Acid dissolves calcium. Bone, being largely calcium phosphate, dissolves in acid. And so the Bog people, the famous preserved mummies whose faces stare up at us from museum cases in Copenhagen and Dublin and London, with an intimacy and an immediacy that 2,000 years should have obliterated, are intact in their skin and their soft tissue and their hair and their fingernails. But their skeletons are gone, dissolved, leaving bodies that are almost comically, disturbingly soft, rubbery, leather-like, flexible in a way that human remains are absolutely not supposed to be. This is important to understand because it defines the preservation paradox of the Bog assemblage. The Bog keeps what it should destroy and destroys what it should keep. It keeps the fragile things, skin, rope, leatherwood, textile, the delicate surfaces of worked metal, and it destroys the durable things, bone hard mineral structures, anything that depends on its calcium content for its integrity. The result is an archive that inverts every assumption that archaeologists bring to the excavation of ordinary terrestrial sites. And this inversion is precisely why the Bog weapons are so important. On dry land, in ordinary soil, an iron object from the Roman Iron Age has almost certainly spent 2 millennia in intimate contact with the oxygen and moisture of its environment. And the result is invariably the same: a process of progressive oxidation that converts the iron of the object into iron oxide, rust. And the rust, being friable and mechanically weak, gradually crumbles and disperses until all that remains, in the best case, is a vague orange shadow in the soil where the object once was, and in the worst case, nothing at all, the surface of the object. And with it, every tool mark, every manufacturing detail, every piece of information about how the object was made is the first thing to go. What this means, in practical terms, is that our understanding of Iron Age European metallurgy has been built almost entirely on the evidence that survived under the worst possible preservation conditions, on the objects that came through 2,000 years of oxidative destruction, with enough of their original structure intact to allow analysis. And what survived, overwhelmingly, is mass. Volume, the shape of things, but not the surface of things, not the internal molecular structure of things, not the precise chemical and crystallographic details that tell the metallurgist, not just what an object is but how it was made. The Bog weapons are different. The Bog weapons come out of the ground with their surfaces intact, with their tool marks, with their weld lines, their pattern structures, their quench surfaces, their molecular architecture. They are, in the most literal sense, the complete record, the full text of a technology that the dry land record preserved only in fragments, only in summary, only in the crude outline of things that tells you the shape of what happened without telling you anything about the depth. Let us be very precise about the error, because precision is what this story demands. The error was not that archaeologists were stupid. The error was not that they were lazy, or dishonest, or ideologically committed to the barbarism narrative. for cynical reasons having to do with the politics of European identity and the justification of colonial hierarchies of civilization. Though those factors certainly shaped the interpretive frameworks within which the evidence was read. The error was structural. The error was built into the evidence base itself, and it was invisible to anyone who didn't understand the differential preservation properties of different soil environments, which, until development of modern environmental archaeology in the second half of the 20th century, was essentially everyone. Here is the core of the problem. When you assemble your understanding of Iron Age European metallurgy from the objects that survive in ordinary terrestrial dry land contexts, and for most of the history of European archaeology, that was the only assemblage available, you are working with a sample that is profoundly biased in a specific and consistently misleading direction. You are working with the objects that happen to be chemically simple enough, or massive enough, or lucky enough in terms of their burial environment to survive intact. You are not working with the objects that were sophisticated. Because sophisticated metallurgy and poor preservation are not independent variables. They are correlated. The more technically advanced a piece of metalwork is, the more likely it is to have precise, carefully engineered surface features that are also the most vulnerable to oxidative destruction. The pattern-welded surface of a complex composite blade, with its alternating bands of different carbon and phosphorus content, producing the characteristic shimmering watered silk visual effect that later European craftsmen would try, and largely fail, to replicate in medieval pattern welding. That surface is the first thing rust takes. The differential oxidation of the different compositional layers produces an accelerated, preferential destruction of precisely the features that make the object interesting. The rust erases the evidence of sophistication before it preserves the evidence of existence. And then an archaeologist picks up the resulting lump of orange-red iron oxide and says, simple, crude, unsophisticated, consistent with the known technological capabilities of a pre-literate Iron Age culture operating without scientific methodology. And they write it down, and someone else reads it and cites it, and the pattern hardens into consensus, and the consensus becomes the textbook, and the textbook becomes what every student learns, and what every student learns becomes what every museum plaque says, and what the museum plaques say becomes what the general public believes, and what the general public believes becomes the cultural background assumption against which new evidence is measured. And if the new evidence contradicts the assumption, the evidence, not the assumption, is the first thing to be questioned. This is not a conspiracy. This is just how knowledge works when it has been built on a sample that is systematically biased in schism that nobody recognized. Because the tools for recognizing the bias did not yet exist. The bog preserved things in a way that made the bias visible. The bog, in effect, gave us the control group. It gave us the same Iron Age European metallurgical tradition, in the same geographic and cultural region, at the same time period, but preserved under conditions that protected its sophistication instead of destroying it. And when you compare what the bog assemblage shows to what the dry land assemblage shows, the discrepancy is so large, so systematic, and so one-directional that it cannot be attributed to regional variation or sample size or any other conventional archaeological explanation. The dry land assemblage shows you what Iron Age smiths could make. The bog assemblage shows you what Iron Age smiths actually made. And what they actually made was extraordinary. X-ray diffraction tells you the crystal structure of a material. Scanning electron microscopy lets you see its surface at magnifications of up to 1,000,000 times, resolving individual atoms in the right conditions. Energy dispersive X-ray spectroscopy maps the elemental composition of a material across its entire cross-section, telling you not just what elements are present, but where they are, how they are distributed, how they transition from one zone to another, what the gradients look like at every scale from the millimeter to the nanometer. When researchers at the National Museum of Denmark applied these techniques to a selection of blades from the Illerup Odal deposit in the 1990s and early 2000s, the resulting datasets were, to use the word that appears in more than one academic paper from the period, stripped of its emotional content, but carrying it nonetheless. Remarkable. The blades were not iron. They were steel. Specifically, they were a complex composite of multiple different steel alloys, each with a different carbon content, arranged in a spatial pattern across the blade, cross-section that was not random, but deliberately and precisely engineered to produce optimal mechanical properties at every point in the geometry of the weapon. The edge zones showed carbon content between 0.6 and 0.8%, the range that modern metallurgy classifies as medium to high carbon steel, capable of being heat-treated to extreme hardness and of holding a cutting edge through sustained mechanical stress. The core zones showed carbon content below 0.2%, the range that produces soft, ductile iron with high toughness and resistance to impact fracture. The transition between these zones was not abrupt. It was graduated, managed, precisely controlled through forging techniques that brought the two materials together at specific temperatures and pressures, and then worked them into intimate contact, without allowing either the high carbon or the low carbon zones to contaminate each other in ways that would compromise their individual properties. The grain structure of the material, the size and orientation of the individual crystalline regions within the steel, showed evidence of deliberate heat treatment. The smiths were quenching their blades. They were heating them to temperatures in the range of 750 to 850 degrees Celsius, temperatures at which the carbon in high carbon steel goes into solid solution within the iron matrix, forming a homogeneous phase called austenite, and then cooling them rapidly in water or in oil or in some quenching medium that left no direct chemical trace, but whose effect was written unambiguously in crystal structure of the finished product. Rapid cooling from austenitizing temperature produces a very specific crystal structure in high-carbon steel. It produces martensite, needle-like crystals of iron with carbon atoms trapped in their lattice in a configuration that makes the material extraordinarily hard, much harder than the face-centered, cubic iron of slowly cooled steel. Martensite is what gives modern high-quality steel cutting tools their edge retention. It is what makes a surgical scalpel capable of holding its cutting geometry through hundreds of uses without requiring resharpening. The Illerup blades contained martensite. 2,000-year-old blades from the forests and workshops of Roman Iron Age Denmark contained the same microstructure as modern precision-engineered cutting tools. And the researchers who first identified that microstructure in the electron microscopic data had to reconcile what they were seeing with everything that mainstream metallurgical history said about when that microstructure became achievable and what it required to achieve. The reconciliation was uncomfortable, and when they published, carefully, methodically, with the hedged and qualified language that academic publication demands, the discomfort propagated out from the specialist literature into the broader archaeological community, and from there, very slowly and very incompletely, into the public narrative of European prehistory. But the full implications of what the electron microscopy was showing have never quite made it into the popular account of Iron Age Europe. And they should have. They should be on the museum plaques. They should be in the school textbooks. They should be the first thing anyone tells you when you ask what the people of pre-Roman Northern Europe could do. They were steel engineers, and they were very, very good. To understand what the Bogsmiths were doing, you have to understand something about iron. That seems simple when you say it, but carries enormous technical depth when you follow it to its implications. Iron, pure iron, is not particularly useful as a structural material. It is too soft. It deforms plastically under loads that a weapon or a tool needs to resist. It does not hold a sharp edge. It is strong in compression but unreliable in tension. The ancient world knew this. The Romans knew it. The Greeks knew it. The peoples of sub-Saharan Africa, who developed iron technology independently and early knew it. And the history of ferrous, metallurgy, is, in one sense, the history of the progressive discovery of what happens when you add small amounts of carbon to iron and then manipulate the resulting material under carefully controlled thermomechanical conditions. Add a fraction of a % of carbon to iron and you get material that is subtly stronger, capable of taking a sharper edge. Add more carbon, up to about 0.8%, and you get steel, a material with dramatically superior mechanical properties that can be further manipulated by heat treatment to achieve a range of hardness and toughness profiles that pure iron cannot approach. Continue adding carbon beyond about 2% and you get cast iron, which is extremely hard but so brittle that it shatters under impact. Useful for certain applications, catastrophically wrong for others. The zone of utility is in the middle. The zone where you have enough carbon to achieve high hardness through heat treatment, but not so much carbon that the material becomes dangerously brittle. This is the zone of steel, and navigating it requires either sophisticated analytical chemistry or, alternatively, such a deep empirical understanding of the visual and tactile and auditory indicators of metal behavior at different temperatures and compositions that you can read the carbon content of a piece of iron the way a master baker reads the state of a dough, by touch, by color, by the sound it makes when you tap it, by the way the surface behaves under specific conditions that you have spent years learning to recognize and interpret. The Blacksmiths were doing the latter. They could not measure carbon content in parts per thousand. They had no spectrometers. They had no analytical chemistry. What they had was something that is, in a certain sense, more impressive. A body of empirical knowledge, so finely calibrated, so precisely transmitted across generations of apprenticeship and practice, that they could produce, consistently and repeatedly, steel with the carbon profile that the electron microscopy confirms, using only the evidence of their senses and the accumulated wisdom of a craft, tradition that had been refining itself for centuries. How did they get carbon into the iron in the first place? Several mechanisms were available, and the archaeological evidence suggests the Blacksmiths were exploiting more than one of them. The most straightforward is carburization, the direct absorption of carbon into iron at high temperatures when the iron is in contact with carbon-rich material. When iron is heated in a charcoal forge to temperatures above approximately 700 degrees Celsius, carbon from the charcoal diffuses into the surface of the iron at a rate that depends on temperature, time, and surface area. Control those variables. Choose the right charcoal, maintain the right temperature for the right duration, manage the surface to volume ratio of the work, and you control the carbon content of the resulting material with a precision that is entirely achievable through empirical calibration, even without formal analytical chemistry. But surface carburization alone cannot produce a blade with different carbon content in different zones. For that, you need a more sophisticated approach, and the Blacksmiths had it. They were working with pre-made stocks of material with different carbon contents, bars of iron that had been subjected to different carburization regimes, producing a range from nearly pure iron to medium and high carbon steel. And they were welding these different stocks together in specific spatial arrangements to produce composited billets with the deliberate cross-sectional profile that the finished blade required. Forge welding is, in principle, simple. Heat 2 pieces of iron to the point where the surface oxides dissolve and the iron itself becomes plastic enough to bond under hammer pressure, then strike. In practice, it is extraordinarily difficult to execute with precision, for several reasons that anyone who has tried it will tell you immediately and at some length. The working temperature window for a successful weld is very narrow, perhaps 50 degrees Celsius on either side of the optimum. Too cool and the surfaces don't bond. Too hot and the iron burns, oxidizing irreversibly and creating slag inclusions that weaken the bond. The color of hot iron changes with temperature in ways that an experienced smith learns to read with great precision, from black through red, orange, yellow, and finally the blinding white of iron, approaching its melting point. But reading those colors accurately in the flickering light of a charcoal forge at a moment when every second of delay costs temperature, and therefore per opportunity is a skill that takes years of immersive practice to develop and a lifetime to refine. Now consider the additional difficulty of welding two materials with different carbon content. High-carbon steel has a lower melting point than low-carbon iron. Its working temperature for welding is different. Its optimal temperature, the point at which it is hot enough to bond successfully without burning, is different. Achieving a high-integrity weld between materials with substantially different carbon contents at a weld line that needs to be mechanically strong and metallurgically sound throughout the life of the weapon requires a level of technical judgment that goes beyond the difficulty of welding similar materials and enters the territory of genuine mastery. The Bogsmiths were doing this consistently at a quality level that the electron microscopy confirms. Weld lines with minimal slag inclusions, clean boundaries between zones of different composition, evidence of a process that was under control rather than subject to the chance variations of inadequately understood chemistry. They were not working by instinct. They were working by knowledge. Here is where the story becomes genuinely strange, because the analysis of the bog blades reveals not just one sophisticated technique, but several, deployed sometimes in combination and sometimes independently, producing a range of blade types that speaks to a metallurgical tradition rich enough to have developed multiple approaches to the same fundamental problem: how to make a blade that is simultaneously hard and tough, and sophisticated enough to understand the relative merits and applications of each. Pattern welding, the technique that produces the characteristic shimmering surface patterns that medieval sword enthusiasts know from the legendary blades of the early medieval period, and that popular culture associates with Japanese katana and the mythologized concept of Damascus steel, is one of these approaches, and it appears in the bog blade assemblage in forms that predate its conventional historical attribution by a significant margin. To produce a pattern-welded blade, a smith begins with a billet composed of alternating layers or twisted rods of iron with different compositions, typically one with higher phosphorus content, which gives a lighter color when the finished blade is acid-etched, and one with higher carbon content, which gives a darker color. These are forge-welded into a composite structure, then manipulated, twisted, folded, cut, and recombined in patterns that determine the visual appearance of the finished blade's surface, while also serving a functional purpose in distributing stresses and creating a material with better fatigue resistance than either component alone. The conventional historical narrative places the origin of pattern welding in Europe in the migration period, roughly the 5th to 7th centuries of the Common Era, and treats it as a response to the specific challenge of manufacturing functional weapons from the low-quality iron that was available in post-Roman Europe, where the supply chains and technical infrastructure that had sustained Roman metalworking had collapsed. But pattern welding appears in the Illerup-Odal assemblage. It appears in the Thorsberg assemblage. It appears in bog blade finds from Ireland and Britain that have been dated to the late pre-Roman and early Roman Iron Age. It appears, in other words, in contexts that predate the migration period by 2 to 3 centuries, in a region where Roman supply chain collapse cannot be invoked as an explanatory factor because Roman supply chains never extended to these latitudes. The Iron Age smiths of Northern Europe did not develop pattern welding as a workaround for poor quality materials. They developed it as a deliberate manufacturing technique for producing a specific class of superior blade. And the fact that later, smiths of the migration period independently arrived at similar techniques in response to different pressures is testimony to the elegance and power of the approach, not to its origin in that later period. The comparison to Damascus steel, to the legendary watered steel of the medieval Islamic world that drove European crusaders and traders to extraordinary lengths to obtain, and that remained a subject of metallurgical mystery well into the modern period, is not casual, and it is not merely visual. True Damascus steel, produced from the Woot steel ingots of South Asia by smiths in the workshops of Syria and Persia, achieved its exceptional properties and its characteristic surface patterning through a mechanism that modern materials science has only recently fully elucidated: the formation of iron carbide nanotubes and nanowires within a fine-grained steel matrix produced under very specific thermochemical conditions during the production of the Wootz ingot. The Bog blades do not contain Wootz-type Damascus microstructures. Their mechanism is different, but their functional achievement. A blade with dramatically superior mechanical properties produced through deliberate, sophisticated manipulation of the carbon-iron system occupies the same category of achievement, and the surface patterns that phosphorus-rich and carbon-rich iron produce when forge-welded and manipulated in the Bog blade tradition, and then revealed by the acid of the Bog environment that acts as a natural etching agent, are visually and conceptually analogous to the patterns of Damascus steel in ways that are not coincidental. Different traditions, same depth of knowledge, same category of mastery. The Iron Age smiths of Northern Europe were not imitating Damascus. They were arriving independently and through their own centuries of empirical investigation at the same fundamental insight: that the beauty of a blade and the excellence of a blade are not separate things, that the surface pattern which records the process of its making is simultaneously aesthetic and functional, and that a blade which has been made with sufficient knowledge and care will announce that knowledge and care in every aspect of its appearance. The energy dispersive X-ray spectroscopy analyses of the Illirup blades revealed something beyond the carbon distribution profile that was already striking enough. It revealed trace elements, minute quantities of metals other than iron, present in concentrations of a few hundred parts per million, that had survived the 2,000-year preservation in the bog and were still measurable in the modern laboratory. Trace elements in iron are geochemical fingerprints. They are the chemical signature of the ore deposit from which the iron was smelted, reflecting the specific mineral chemistry of the rock in which the iron ore was embedded. Manganese, vanadium, nickel, cobalt, molybdenum. These elements occur in iron ore deposits at levels that vary characteristically from one geological formation to another. And while ancient smelting processes could not isolate or deliberately concentrate these elements, they could also not eliminate them. They passed from ore to smelted iron, and they remain in the iron across millennia, waiting to be read. Modern isotopic and trace element analysis techniques, laser ablation, inductively coupled plasma mass spectrometry, being the most powerful currently available, can read those geochemical fingerprints with sufficient precision to trace the iron in a finished artifact back to the ore deposit from which it came. This is the same class of technique used to trace the origin of wine, to authenticate artistic masterpieces, to track the provenance of conflict minerals in modern supply chains. It is a chemistry of origins, and when it is applied to the bog blades, it tells a story that is as remarkable as the story of their metallurgical sophistication. The iron in the Illirup blades does not all come from the same source, different zones of the same blade. Remember the composite structure, the deliberate arrangement of different compositions across the cross-section, come from iron with different trace element profiles, meaning they were smelted from ore that came from different geological sources that have been tentatively identified as lying in geographically distinct regions of Scandinavia and the continental European interior. The high-quality, manganese-rich iron that produces the best edge properties, the iron that was used in the high-carbon edge zones of the composite blades, appears to have come from specific ore deposits whose geochemical properties made them superior for steelmaking in ways that the smiths had identified empirically over generations of working different ore stocks and observing the differences in behavior. They had mapped the iron without formal geology, without sampling campaigns and chemical analysis and computer databases of elemental signatures. They had developed through the accumulated experience of generations of smelters and smiths, a practical knowledge of which ore deposits produced iron that behaved in which ways, and they had organized their trade networks to ensure access to the specific ore stocks that their most demanding applications required. This is not primitive. This is industrial. This is not a tribe stumbling across useful rocks. This is a technologically sophisticated community with systematic knowledge of materials science, a supply chain organized around that knowledge, and the economic and social infrastructure to sustain, both over periods of time long enough to allow the knowledge to accumulate and the supply chains to stabilize. And when you understand that the weapons found at Illirup Odal were not produced locally, but assembled from components with different provenance, forged by smiths, who were drawing on iron stocks from regions hundreds of kilometers apart, selected and transported specifically because of their known superior properties. When you understand the scale of the economic and informational network that a single composite bog blade represents, the narrative of the primitive barbarian does not merely become implausible, it becomes absurd. Here is the fact that haunts the archaeology of the Iron Age bog deposits. and that no amount of technical analysis of metallurgical microstructures and trace element profiles can fully explain, because it is not a technical question but a human one. Almost every sword found in the bogs of Northern Europe has been deliberately destroyed before deposition, not accidentally damaged, not lost in battle and later swept into a waterway. Deliberately, effortfully, intentionally bent or broken or twisted into a shape that renders the weapon non-functional, and then placed. The evidence suggests placed rather than thrown, in many cases, in the bog with what appears, from the spatial organization of the deposits, to have been careful intention. At Illerup Odal, the sword blades are bent at angles that required significant mechanical force. In some cases, the application of leverage against a stone or anvil. In other cases, for the heavier blades, what must have been a coordinated effort by multiple individuals. The blades are not simply folded in half. They are bent in specific ways at specific points, producing shapes that recur across the deposit and across comparable deposits at other sites. Shapes that suggest not random destruction but a consistent, repeated ritual action with a specific visual and perhaps symbolic vocabulary. At Thorsberg site in Schleswig-Holstein, the weapons are not merely bent but systematically deconstructed. Scabbard components separated from blades, sword belts cut from their fittings. The entire assemblage disaggregated in ways that mirror in reverse the process of assembly and equipping a warrior for battle. What was put together for war was taken apart for the offering. At Nydam Mose in Denmark, the site of one of the most spectacular Iron Age discoveries in Scandinavian archaeology, a 23-meter clinker-built boat, the oldest of its type in the world, preserved in the peat with its oars still in position. The associated weapon deposits show the same pattern. Deliberate destruction, deliberate placement, and an organization of the material that suggests the existence of a ceremony with specific stages, specific roles for specific participants, and specific outcomes that were considered essential for the purposes that the offering was meant to serve. The scale of the economic sacrifice represented by these deposits is almost impossible to overstate. A single composite bog sword, a blade of the technical quality we have been discussing, with its carefully managed carbon distribution, and its imported high-quality iron, and its forge-welded composite structure, and its heat treatment, and its pattern welding, represents an investment of labor, material, and knowledge that the economic historian Marcus Jorgensen has estimated in an analysis published in 2019 as roughly equivalent to 6 months of full-time skilled labor for a single specialist craftsman. The Illerup Odal deposit contains hundreds of such blades. These communities were throwing their most sophisticated and economically valuable manufactured objects into the swamp. On purpose. Repeatedly. Across 3 centuries. Why? There is a concept in the anthropology of religion, developed in different forms by Marcel Mauss, Marshall Salins, and more recently by David Graeber in his extraordinary work on the history of value and debt, that might help us understand what was happening in the bogs. If we are willing to think carefully enough about what exchange and sacrifice and destruction actually mean in economies. where the relationship between the human world and the non-human world is not understood as a metaphor, but as a literal, ongoing, transactional reality. The concept is this, that sacrifice is not waste. Sacrifice is investment. Sacrifice is a form of exchange in which what is destroyed in the visible, human-accessible world is simultaneously created in the invisible, divine-accessible world. And what is created there has value in ways that what was destroyed cannot, precisely because it has passed through the transformation that destruction represents. In this framework, the bent sword is not the end of the sword's utility. It is the beginning of a different kind of utility. The bending, the deliberate, effortful, ritualized destruction of the weapon's function in the human world is the act that transfers the weapon's value from one economy to another. It removes the sword from the economy of human exchange, where its value is denominated in iron and labor and fighting capacity, and introduces it into the economy of divine exchange, where its value is denominated in something the surviving sources call by many names: favor, protection, reciprocity, the ongoing maintenance of the relationship between the community and the powers upon which the community's continued existence depends. The Iron Age communities of Northern Europe were not monotheists. Their cosmology was not organized around a single transcendent deity with a comprehensive moral vision and an interest in being propitiated through correct behavior. Their religious world was pluralistic, contextual, and intensely practical, a world populated by powers whose specific domains and specific demands were known through tradition and through the accumulated experience of what had worked before, and whose relationship to the human community was not one of unconditional benevolence, but of ongoing reciprocal obligation. Water was a medium of communication with specific categories of power. The powers of transition, of boundary, of the underworld that lay beneath the visible surface of the earth. Depositing objects in water was not discarding them. It was addressing them to the powers that water represented. Powers of fertility, of death, of the cyclical return that death makes possible, of the warrior spirits that needed to be fed and honored and maintained in their continuing relationship with the living community. The Tacitus account of the Germanic tribes, for all its political distortions, preserves a detail that is relevant here. He describes the sacrifice of weapons to specific divine powers, to Tiwaz, known to the Romans as Mars, the god of war and the sky, and the ordering of communities through the resolution of conflict. And he describes the practice as ancient and widespread, observed across the Germanic world from his perspective as a writer in the late 1st century CE. The bog deposits confirm that this was not Roman exaggeration. Weapon sacrifice was real, was widespread, was sustained, and was organized on a scale that implies not individual acts of private piety, but coordinated community events with significant logistical and economic dimensions. The Illerup Odal deposit, in particular, appears to represent not the accumulated offerings of private individuals over centuries, but the equipment of specific defeated armies, the weapons, armor, and personal equipment of warriors killed in battle. systematically collected from the battlefield and deposited en masse in organized ceremonies that may have followed specific military victories. If this interpretation is correct, then the bent swords of Illirup are not just votive offerings in the ordinary sense. They are war trophies transformed into divine tribute, the material substance of military victory converted, through the chemistry of ritual destruction and watery deposition, into the currency of ongoing divine favor. The sophistication of this practice, the organizational complexity of collecting thousands of weapons from a battlefield, transporting them to a sacred site, categorically organizing them, systematically destroying them in a ritually correct manner, and depositing them in the water in a spatial arrangement that preserves their categorical organization, is not, it should be noted, the kind of sophistication we associate with primitive brutes. It is the kind of sophistication we associate with organized, hierarchical, administratively capable communities, with sophisticated logistical systems and detailed ideological frameworks for making sense of violence and victory and the obligations that success in war creates. They were not throwing their swords away. They were making the most important investment available to them in the currency that mattered most. The blacksmith in pre-industrial societies across the world was not simply a craftsman. He, and in most cultures, the smith was almost universally male, though exceptions existed, and were often heavily mythologized, occupied a social position that was simultaneously elevated and marginalized, simultaneously powerful and dangerous, simultaneously revered and feared. He was the person who transformed the inert substance of the earth into the objects that made civilization possible: tools, weapons, agricultural implements. And the transformation he accomplished was understood in most pre-scientific cosmological frameworks as analogous to, or connected with, or in some cases literally identical to, transformations that were otherwise the domain of the supernatural. The smith worked with fire, with extreme heat, with materials that behaved in ways that were not intuitively explicable without a detailed technical understanding that most community members did not possess. He heated metal until it glowed, until it achieved colors associated with the divine, with the sun, with the forces that exceeded human scale, and then he struck it, and it changed. The transformation was visible, immediate, dramatic, and in its technical dimensions completely opaque to anyone who had not spent years learning what was actually happening and why. This opacity was not accidental, and it was not merely the result of the technical complexity of the craft. It was, in many cultures and at many historical moments, actively maintained. The knowledge of the smith was secret knowledge, transmitted through structures that protected it from unauthorized access and ensured that it remained the exclusive property of the social group that had developed it. The evidence for smithing guilds, for organized, institutionalized bodies that controlled access to metallurgical knowledge and managed its transmission across generations in Iron Age Europe is necessarily indirect, because guilds of the kind we are discussing left no written records, no legal charters, no membership lists. What they left are patterns in the archaeological record, patterns of smithing site distribution that suggest deliberate separation from settlement centers, patterns of grave goods that distinguish smithing specialists from warrior elites and agricultural communities through specific object associations, patterns of the concentration of technical expertise that imply a form of social organization around the craft. Iron Age smithing sites in Scandinavia and northern Germany are consistently found at the margins of settlement areas rather than at their centers. The forges are not integrated into the domestic architecture of the village or the longhouse community. They are separate, often physically isolated, frequently associated with specific natural features, springs, streams, elevated ground, that carry specific cosmological significance in the religious geography of the communities that built them. This separation was not purely practical. Yes, there were practical reasons to keep forges away from domestic structures. The fire risk was real, the noise was significant, the smoke was substantial, but the degree of separation that the archaeological record shows, the deliberate physical isolation, the specific siting near cosmologically significant features, the association of smithing sites with depositional practices that imply the site itself was understood as sacred or liminal, goes beyond the practical and enters the symbolic. The forge was a threshold space, a place that existed between the human world and something else, a place where the transformations that took place were understood as partaking of a power that ordinary human activity did not routinely access. And the smith was the gatekeeper of that threshold, the person whose technical mastery and, implicitly, whose relationship to the powers that governed the transformational chemistry of fire and metal made the transformations possible. In this social context, the transmission of metallurgical knowledge was not simply a technical education. It was an initiation. The apprentice smith did not merely learn techniques. He was inducted into a body of knowledge that was simultaneously technical and spiritual, simultaneously empirical and cosmological, that carried obligations of secrecy and specific behavioral requirements that marked him as belonging to a category of person different from, and in important respects set apart from, the ordinary members of the community. The myths of the divine smith, Hephaestus in the Greek tradition, Goibniu in the Irish, Wayland, Volunder in the Germanic and Norse, encode this understanding in narrative form. The divine smith is always at once a figure of extraordinary power and a figure of marginality, isolation, or physical difference. Hephaestus is lame. Wayland is captured, imprisoned, mutilated, in ways that mark him permanently as different. The divine smith can make anything, can produce objects of miraculous power that exceed what ordinary craftsmanship should be able to achieve. But he exists at the edge of the divine community, rather than at its center, his power recognized, but his person kept at a careful distance. These myths are not merely stories. They are social maps. They describe the actual position of the human smith in the community, powerful, necessary, feared, isolated. And they make sense of that position by placing it in a cosmic framework in which the smith's special relationship to transformational power is not an accident of technical expertise, but a feature of his nature and his relationship to the divine forces that govern fire and metal and making. The knowledge these myths encode, the formulas for carbon manipulation, the secrets of quenching and tempering, the geochemical geography of superior ore sources, the specific proportions and techniques of composite welding, was the property of the guild. It passed from master to apprentice in the intimate, embodied, experiential way that tacit technical knowledge always passes. Not through books or formal instruction, but through years of practice and observation and correction and gradual, supervised assumption of responsibility. And when the communities that sustained the guilds were disrupted by war, by migration, by the social reorganizations of the late Iron Age and the early migration period, the knowledge was vulnerable in a way that written knowledge is not. It existed only in the minds and hands of the people who practiced it. It could not be backed up. It could not be referenced if the person who held it died before they had finished transmitting it. It could be lost in a generation, and it was. Not entirely, not immediately, not in a single catastrophic moment that we can point to and say, here. This is where the knowledge ended, but gradually, across the chaos of the centuries that followed the Roman Iron Age, the migration period, the early medieval reorganization of European society, the demographic and economic disruptions of successive waves of invasion and social transformation, the guild structures that had sustained the knowledge were weakened, disrupted, and in many regions destroyed, and the knowledge, deprived of the social infrastructure that was its only means of transmission, faded. What replaced it was not inferior craftsmanship. The smiths of the early medieval period were excellent craftsmen, producing work of great beauty and genuine technical quality within the tradition that they had inherited. But the most sophisticated techniques, the composite structural steelmaking, the controlled carbon distribution, the deliberate microstructure management, those elements of the older tradition were gone from the mainstream, surviving at best in fragmentary, imperfectly understood forms in isolated workshops and occasional individual practitioners, whose names did not make it into the surviving record. The knowledge that had made the Illirup blades possible was buried in the swamp alongside the blades themselves, and it waited there, in the cold and the dark, and the acid peat for 2,000 years, until we developed the tools to read what the metal remembered. We began with a sound, the sound of peat giving way, the sound of something that had been held in silence for 2,000 years finally being given permission to speak. And what it said, what the blade said, in the language of electron microscopy and X-ray diffraction and energy dispersive spectroscopy, was something that the history books needed to hear. The so-called barbarians of pre-Roman Northern Europe were not technologically inferior to Rome. They were technologically different from Rome in ways that the Roman evidence base and the historiographic tradition it spawned systematically obscured. Obscured because the evidence of Roman metallurgy survived well, and the evidence of Iron Age European metallurgy survived poorly. And because the people doing the archaeology brought to their work assumptions about the correlation between literacy, urbanism, and technical sophistication that led them to systematically underread the capacity of the communities whose work they were analyzing. The Iron Age smiths of Illerup, Odal, and Thorsberg and Nydam were producing composite structural steel with controlled carbon distribution profiles. They were forge welding dissimilar alloys with precision sufficient to produce weld lines that have survived 2,000 years of bog chemistry without structural failure. They were heat-treating their blades to produce martensitic microstructures in the edge zones, while maintaining the tougher, more ductile microstructure of the core zones. They were pattern welding to produce blades with superior fatigue resistance and with the shimmering surface patterns that spoke in the visual language of their cultural tradition, of mastery and care and the intervention of something that exceeded ordinary human capacity, of the Smith's Guild knowledge, and behind it, of the divine forces that the Smith's marginal, liminal, thresh-crossing social position gave him privileged access to. They were doing all of this with no written records, no formal chemistry, no thermometers or spectrometers or analytical instrumentation of any kind. They were doing it with fire and iron, and the accumulated, embodied, transmitted empirical knowledge of a guild tradition that had been refining itself for centuries, with the kind of knowledge that takes the longest to develop, is the hardest to transmit, and is the most catastrophically vulnerable to the disruption of the social structures that sustain it. And they were doing it better in certain specific technical dimensions than the Roman smiths, whose work has been the conventional benchmark for this period. Roman iron technology was, in many respects, impressive. The Roman army ran on iron nails, held the legionary fortresses together, iron tools built the roads, iron weapons equipped the most professional military force in the ancient world. Roman smiths understood iron and steel, and their understanding was backed by the resources of an imperial economy with sophisticated supply chains, large-scale production facilities, and at least some degree of systematized quality control. But Roman military iron was, with exceptions, produced for scale rather than for individual excellence. The legionary gladius was a good sword, well-made, functional, fit for purpose, but it was not an Illerup composite blade. It did not have the deliberate cross-sectional carbon gradient of the best bog swords. Its heat treatment was less consistent. Its microstructure showed less evidence of deliberate management. The Iron Age smiths of Northern Europe, working in smaller workshops for smaller communities with higher per-unit investment in each blade, were operating at the other end of the quality scale. Trade-off: they were producing fewer objects of higher individual sophistication. And in the specific technical domain of composite blade construction and microstructural management, they were, at their best, ahead. The barbarians had better swords than Rome. Not all of them, not on average, but the best of them, the masterpieces of the ghost guilds, the products of traditions that had accumulated knowledge for centuries, were, by the metrics that matter to a person who is trying to survive a battle, superior. The bog blades are not an isolated anomaly. They are the most visible, most dramatically preserved expression of a broader pattern of technical sophistication in pre-Roman Northern European culture that has been consistently underestimated. And only recently, through the accumulation of modern analytical methods and the willingness of a new generation of archaeologists to challenge inherited assumptions, beginning to be assessed at its actual level. The Celts of Central Europe, the Latinian culture that dominated a vast stretch of continental Europe from roughly 450 BCE to the Roman conquest, produced iron technology that modern analysis has shown to be significantly more sophisticated than the conventional historical narrative acknowledged. Latin swords found in dry land contexts were long dismissed as soft, poorly made, prone to bending on impact, a criticism based on Caesar's commentary about Celtic warriors having to stop in the middle of battle to straighten their bent blades. Modern metallurgical analysis of Latin blades suggests that the bending was not a product of technical incompetence, but of a deliberate choice to prioritize toughness over hardness in blade designs, intended for a specific combat style, and that the best Latin iron is, in its own technical parameters, considerably more sophisticated than the Roman commentary acknowledged. The iron plowshares of Iron Age Britain, a technology whose diffusion through the British Isles is conventionally dated to the arrival of Roman agricultural practice, appear in some pre-Roman contexts at levels of technical sophistication that suggest indigenous development rather than importation. The ironworking tradition of the Norican Alps, the region of what is now Austria and Slovenia, that produced the iron ore known in antiquity as ferrum noricum, specifically prized by Roman weapon smiths for its superior quality, was a pre-Roman development built by Celtic metallurgists who had identified the specific geochemical properties of the Norican ore deposits and developed the technical infrastructure to exploit them. The pattern is consistent, and the conclusion it points to is not comfortable for historiographies that have built their narrative of European development around a model of progressive, one-directional technical advance from primitive barbarism to civilized sophistication, a model in which Rome is the peak, the peoples Rome conquered or interacted with are the lower rungs of the ladder, and the period before Rome is the beginning of the climb. The actual pattern is not a ladder. It is a landscape, a complex, varied, geographically and temporally uneven landscape of technical achievement and failure, of knowledge accumulated and knowledge lost, of traditions that flourished and traditions that collapsed, of innovations developed in isolation and innovations that spread through networks of exchange and contact, of peaks and valleys that do not arrange themselves into the clean, progressive narrative that intellectual convenience and political ideology have historically preferred. Iron Age Europe had peaks. Some of those peaks were in places and among peoples that the Roman-derived historical tradition has classified as primitive. Some of the knowledge those peaks represented was lost, not transcended, not superseded by something better, but genuinely lost, buried in the peat of the northern bogs along with the bent and sacrificed masterpieces that embodied it. We are only now beginning to understand what we lost. The study of the bog blades is not merely historical. It is not merely a project of recovering and correctly valuing a lost chapter of European technical history. It has practical implications for modern materials science that are, in certain specific ways, generating genuine research interest. The composite structural approach of the Iron Age smiths, the deliberate arrangement of materials with different mechanical properties in specific spatial patterns to produce a blade that is optimized across its geometry, is, in principle, the same approach that underlies modern composite materials engineering. Carbon fiber, reinforced polymer composites, metal matrix composites, functionally graded materials. These are all at the conceptual level, the same idea that the Illerup smiths were executing in iron and steel 2,000 years ago. Different materials with complementary properties combined in architectures that express the properties of each where they are needed and suppress them where they are not. The specific mechanisms are different. The scales are different. The materials are different. But the insight that the way you arrange materials matters as much as, or more than, the materials themselves is the same insight arrived at by different routes across a 2,000-year gulf. Modern researchers studying functionally graded materials have, in some cases, explicitly cited the Iron Age composite blade tradition as a historical precedent, as evidence that the functional grading approach was independently discovered and successfully implemented by pre-industrial craftsmen working from empirical knowledge rather than material science theory. This citation is not merely decorative. It serves the genuine epistemic function of demonstrating that an approach which might seem to require modern theoretical foundations can, in fact, be developed through systematic empirical investigation without those foundations. The bog blades are, in this context, proof of concept. They prove that the composited approach works, that deliberately arranging zones of different carbon content in a blade cross-section produces a weapon that performs better than a uniform alloy blade. Not merely in theory, but in 2,000 years of field testing. And they prove it without the benefit of the theoretical framework that modern materials science would use to predict and explain the result. There is a lesson here about the relationship between empirical knowledge and theoretical knowledge that goes beyond the specific case of Iron Age iron technology. It is a lesson about how knowledge is actually built. Not always from the top down, from theory to application, from scientific principle to practical realization, but sometimes from the bottom up, from accumulated observation to reliable practice to the gradual, hard-won formulation of principles that explain what the practice has known for generations. The Iron Age smiths did not have the theory of carbon diffusion in iron, but they had, through centuries of observation and refinement, a reliable practice that produced the results that the theory predicts. They arrived at the destination by a different route, and arriving by a different route does not make the destination less real. We carry as a civilization a powerful and largely unexamined assumption about the relationship between time and knowledge. We assume that earlier means less, We assume that the people who came before us understood less than we do, could do less than we can, had access to less truth about the nature of the world than our current scientific establishment commands. We assume this because in certain specific and important ways it is true. We have more information, more analytical power, more systematic knowledge of more domains of reality than any previous human civilization. This is real and it matters. But the assumption extends in ways that are not always carefully examined, beyond the domains where it is justified, and into areas where it produces systematic blindness. We assume not just that we know more, but that people who came before us were, in some more general sense, less capable, less intelligent, less observationally acute, less able to derive reliable, practical knowledge from systematic attention to the behavior of the world. And this extended assumption, the assumption of general ancestral incapacity, is not supported by evidence and is regularly contradicted by evidence, and the Bog Blades are one of the most dramatic and well-documented of those contradictions. The Iron Age smiths were not less intelligent than modern material scientists. They were operating under different constraints with different tools in different social contexts. And they developed, within those constraints and through those tools, a level of practical mastery in their specific domain that modern science, when it finally looked closely enough to see what they had accomplished, was forced to acknowledge as genuine, as sophisticated, and as, in certain specific, technical dimensions, surpassing what their supposedly more civilized contemporaries could achieve. Technology does not move in a straight line. This is the lesson that the Bog teaches. Technology expands and contracts and is lost and is rediscovered and moves laterally and goes deep in one place while remaining shallow in another. And the relationship between technical sophistication and the other markers of what we call civilization, writing, urbanism, political complexity, long-distance trade, is not a simple correlation. You can have writing without steel. You can have steel without writing. You can have cities without running water, and running water without cities. The people of the Iron Age bogs had neither writing nor cities, but they had something that the Roman historians who dismissed them as barbarians did not give them credit for, and that the modern scholarly consensus has only recently begun to fully acknowledge. They had a science. Not science in the formal, institutional, explicitly theoretical sense that we associate with the modern scientific enterprise, but science in the original, deepest sense of the word. Systematic, empirical, cumulative, transmittable knowledge of the behavior of the natural world, applied with skill and precision to the production of real outcomes. They bent the iron to their will. They read the ore. They managed the carbon. They timed the quench. They folded the blade. They knew, in the way that mastery always knows, not through the mediation of conscious theory, but through the immediate, embodied, reliable recognition of what works and what doesn't and why. They knew what they were doing. And then they threw their finest work into the swamp, bent and broken, and transformed into currency for a divine economy that modern rationalism has no framework for understanding. The stone knows. The iron knows. The peat has been holding the answer for 2,000 years, and every blade that comes out of the dark acid ground into the clean light of a modern laboratory is telling us the same thing, over and over, in the language of crystal structures and trace elements and deliberate microarchitecture. We were here. We understood. We were not what you thought we were. The next time someone tells you that ancient peoples were primitive, that the gap between us and them is a gap of intelligence, of capacity, of fundamental human capability, I want you to think about the Illirup swords. I want you to think about what it took to produce them. The knowledge of carbon chemistry without analytical chemistry, the mastery of heat and time and material behavior without instruments, the trade networks that brought superior iron from hundreds of kilometers away to workshops where guild masters encoded their understanding into composite blades that modern science had to look at twice before it believed what it was seeing. I want you to think about the bent blades, about the communities that produced their most extraordinary material achievements, and then, deliberately, ceremonially, with full knowledge of the economic and technical value of what they were, destroying, transformed those achievements into a different kind of values, a spiritual currency, divine tribute, the ongoing payment of a debt to the powers that their cosmology told them sustained the world. And I want you to ask yourself what assumptions you're carrying about human capability and human knowledge and the relationship between time and progress. Assumptions that might, if you put them under an electron microscope, turn out to be as wrong as the assumption that pre-Roman Europeans were incapable of sophisticated metallurgy because the bog is patient, the iron is patient, the knowledge is waiting in the dark beneath the surface of what we think we know. And every time we look closely enough, every time we bring the right tools and the right willingness to be surprised by what we find, the story changes. What assumptions are you sitting on right now? Tell us in the comments. We read every single one. And if this kind of history that doesn't let the comfortable narrative go unchallenged, history that follows the evidence into the uncomfortable places where the textbooks went wrong, if that's the kind of history that speaks to you, then subscribe and turn on the notification bell and come back next week, because we are just getting started. The Bog has more to say.